Okay, hello everybody. My name is Germán García, and this is lecture 6 of time series analysis. Today we're going to be taking a deeper look into linear models, and we are going to set the basics for what nonlinear modeling is, which we will occupy lectures 7 and 8 with most likely. So there we go. This besides parametric methods, which are the ones we have studied already, there are non-parametric methods, namely we can do moving window estimates. High frequency financial data can be modeled without parametric models, and then the use of open, high, low, and closing prices can actually work better if we use certain non-parametric models. And so the first example of this is the moving windows method. It's a really simple approach to capture time varying feature of the volatility. The problem with this is, basically here what we do is determine a window and state that our prediction is going to fall mostly in that window. And as you can guess at the first sight, it's pretty hard to estimate the size of the window correctly. So we could end with a model with an unrealistically tight window that doesn't work at all. So in order to see this, I'm going to upload the script mvwindow.r, which is within the date of the course, so you can have a really good vision on that. In order to do that, just follow these instructions. You have done it already with all the commands for this course, and then please take care with this. And so this model actually what gives us is the volatility stored within the variance, within the standard deviation. Sorry. Now let's assume that we want to estimate the monthly volatility of a stock return. Our data will be the daily returns. So what we want to do is basically transcend from days to months to amplify our predictions. So we're going to let RT super M be the tth month log return, and RTY with y varying from 1 to n be the n daily log returns within the tth month. I mean, this I goes basically from 1 to 31, and t is the number of the month. Using properties of log return, we have this interesting property over here, and assuming that both conditional variance and covariance exist, we have this nice property over here, where the conditional variance is given by a linear combination of the previous conditional variance and the double covariances. So as you have seen, this can be quite hefty depending on how many models we use and everything. So there is a further assumption that we can do. If our series of previous returns is a white noise series, then the variance of the month, the monthly variance of the tth month, conditioned to this is actually the number of days times the variance of the first day. Okay, this would make it extremely convenient that the RTY would be a white noise series. In this case, VART1 could be estimated from the daily returns using this nice formula here. This is sample variance, nothing else, where RT with a hat is the sample mean of the daily log returns in this month, calculated this way. And so we could say that the estimated monthly volatility is basically this super really nice sum over here. If the series of daily returns is not white noise, but it follows an MA1 model, which has the advantage of extreme simplicity, then our variance can be estimated in this way: n times variance of RT1 plus 2 times m minus 1 covariance of RT1, RT2. What we're doing here is, instead of one coefficient, we have to already start considering covariances. And so our variance can be estimated in this way. If you remember, all this part corresponds to here. And the rest is basically m minus 1 times a covariance, which is easy to both understand and compute. Advantages of this is super simple. Weaknesses for this, models for daily returns RTY are unknown, and typically a trading month has 21, 22 days roughly, which means sample size is small, which implies predictions are not good by definition. Here we have plots of estimated monthly volatility for Standard & Poor's 500 index. In the first plot, we assume that the daily log returns form a white noise series. In the second one, we assume that the daily log returns follow an MA1 model, and in the third one, we use monthly returns and a generalized arch model 1-1. As you can see, these spikes get a bit uncontrolled, but here in the GARCH 1-1 model, things get a bit flatter. And so, if we assume the sample mean to be 0, then we can estimate the sample variance like this, as basically the cumulative sum of squares of daily log returns. So we can apply this idea to intraday log returns and obtain what is called realized integrated volatility. If we assume that the daily log return follows this form, then this estimate over here, which we would use to estimate sample variance, is actually called realized volatility. This has an advantage, which is its simplicity. Basically, a realized volatility is just one component, is a linear combination of squares. We really can't ask for much more in terms of simplicity. And it also uses the daily information from all days instead of only 1 or 2, as the previous cases did. However, it has two weaknesses. Mostly the effects of market microstructure noises are ignored, and overnight volatilities are overlooked. So that's pretty big, actually. Now, dwelling a bit deeper, let delta be the sampling interval, and so as the sampling interval goes to 0, the sample size goes to infinity. This makes sense, really. Under the assumption that the log returns in this interval, for example, 5-minute returns, are independent and identically distributed, then this nice sum over here converges to the variance of the daily return. This is called quadratic variation. Then now, somebody could be wondering why a smaller delta provides a bigger sample size. In this case, let's figure out the 5-minute returns. Instead of taking one daily month return, we took 1 month return every 5 minutes. That gives us 288 estimates each day. That's already big, right? If instead of 5 we take 1 minute, we'll get 1440, which is starting to be interestingly big. So we can always pick smaller intervals and use this quadratic variation property to get better estimates. However, in practice, there are some microstructure noises that can affect our estimate. This is fundamentally the bid-ask bounds. In fact, it can be shown that as the interval goes to 0, the observed sum of squares, this sum of squares, goes to infinity. You can be wondering why. The reason is because the returns are not bounded. And so if you sum arbitrary big amount of squares of things that are not bounded, you really don't know. You can't make that converge to anything because it mostly is an infinite sum. And so, what can we do then? Like if taking smaller returns give us, I mean, slower intervals give us better samples at the cost of our potential observed variance going to infinity, what can we do? Okay, there are two approaches. First one, optimal sampling interval. It was given in 2006 by Bundy and Russell, and so we should find an optimal interval. Equivalently, the optimal sample size, which is exactly 6.5 hours out of the day, it can be chosen in this way. This is quite a really interesting one. It has these properties here. If you are familiar with this, this is mostly a kurtosis coefficient with a 1/3 exponent. So this is kinda. This looks like the fourth moment of a variable with mean 0, and this is the second moment with the only particularity of this coefficient. This is exactly the second moment. This is a bit twisted, but this is essentially there. Here m is the number of daily quotes available for the underlying stock. I mean how many instances of data you pick here, and these results are computed from the midpoint of the bid and ask quotes. You take bid plus ask divided by 2, that's your estimate. That's your estimated return, sorry. Second approach, it's called subsampling. We take delta between 10 and 20 minutes, compute integrated volatility for each of the possible return series, and then take the average. In fact, the authors propose something called two scales realized volatility, which has this form. Here, ARV sub I denotes the average realized volatility of time interval I. An is a real number that tends to 1, and B sub n is A sub n times this exponent, which is basically n minus k minus 1 divided by k, and all of that divided by a minus j minus 1 divided by j. Here, it's important to consider that n is the number of transactions within the day, and j can be either 1 or much smaller than k. We are talking about several orders of magnitude smaller. When j equals 1, the second term is regarded as the estimate of the noise, and when k is much larger than j, the second term is typically very small, like very small. So, different thing we can do. A different approach for estimating volatility is the use of daily open, high, low, and close prices. We're going to call them like this: C for close, O for open, F for fraction of the day, when the day goes basically from 0 to 1, where 0 is 0000 and 1 is 23:59 p.m. H for the highest, L for the lowest, and F, big F, for public information available at the proper time. Here you have a time plot for the price over time for the TF trading day. Scale is arbitrary, please forget it, it's just an example. So the conventional variance is defined in this way. Or alternatively, we can take it in this way if we are only using an interval one. If we use more of them, then the shape of this changes a little bit. It becomes opening price minus closing price at the previous time squared, and in the other way, closing minus opening, where F is fraction of day. Here it is very important that F, I mean the fraction of the day, is neither 0 or 1, because otherwise one of these two just goes to 0, so this goes to infinity, and a variable with infinite variance is generally undesired. Some have interesting properties, but they're generally undesired. The second one is calculated in this way. 4 times logarithm of 2 is mostly the inverse of this amount. The third one, like this, and well, it gets a little bit more complicated with each steps. Out for volatility, I will directly go for this, either this and this alternative. In the book, there is a more precise estimator for the fourth one. As you can see, 0, 1, 2, 3, and 5. The fourth one is estimated in the book, but it's actually pretty close to this. Like they are actually very similar. So a volatility estimator have certain level of efficiency, and it can be measured using this estimator. It's basically variance at the 0th moment divided by variance of this at the ith moment. Garaman and Klaus found that this estimator is approximately 2, 5.2, 6.2, 7.4, and 8.4 for these coefficients respectively for the simple diffusion model entertained. This is a concrete model. I'm not considering data, but in this exact model, if you can see, the fourth one is not there, and the reason is this, because it is pretty close there. So you can actually use sigma with a hat squared sub 5 to estimate sigma with a hat squared with 4. So for logarithm volatility, one should take the logarithm of these prices, open, high, low, and close. And so let's suppose there are n days of data available and the volatility is constant over a period. Yang and Zhang recommend this estimate here as a very robust estimator, where the coefficients go as follows. Sigma sub 0 squared is basically what you might expect it to be. Is the second moment of variable O sub t. Sigma c squared, sigma c squared is the second moment of variable c sub t, and this is a sort of correlation coefficient here. And finally, yes, we have this coefficient k, which is 0.34 divided by 134 plus n minus 1 divided by n plus 1 divided by n minus 1, which makes sure this never goes to 0. However, if we have exactly one data, this goes to 0, this fraction is infinity, so this coefficient k is 0 and this is 1. So it doesn't break the reasoning if here we have only one sample of data, although it's probably not as useful. Now, for a quick remark, we should consider the stock split. Some people are using daily range. For log returns, this range is defined as the logarithm of the highest minus logarithm of the lowest, or logarithm of the quotient, as you prefer. The reason why is related to duration models to be discussed later when we go with high frequency data. There are different approaches to volatility estimation, but it's rather early to assess the impact of this. This is in a very early stage. It's a pretty complicated topic itself, so advances are doing slow and steady. So it's a good idea in general to use more information, and however, if you use it, you should consider some institutional effects, serial correlations, and all that, because adding more data could be beneficial, but the corresponding model altering effects could actually mess up your measures and give you a worse estimate on how to do predictions with this. So next thing we're going to discuss is a small introduction to nonlinear models. And first we're going to answer the very first question that appears. Does nonlinearity exist in financial time series? Short answer, yes. Long answer, especially yes in volatility modeling and especially yes in high frequency data analysis. Here we're going to focus on very simple nonlinear models and neural networks which work mostly with logarithms and things that are basically reasonably easy to conceive, so we won't go into anything too long or complicated. So for the first time, what is a linear time series? This is a linear time series. This is a constant. These are real numbers, with the first one being exactly 1. And a sub t minus y minus I, is a set of independent and identically distributed variables with mean 0 and variance their variance, non-infinite. So we're going to let f sub t minus 1 denote the information available at time t minus 1. And so conditional mean mu sub t can be calculated in this way. We're going to call it g of ft minus 1. And the conditional variance can be calculated in this way, and we're going to call it h of ft minus 1. And so g and h are both well-defined functions. This is positive because it's defined as the square of something real. And for a linear series, g is a linear function of ft minus 1 and h. Statistics literature generally focus on function g, but financial econometrics generally focuses on h. So you might as well take a small grasp on both. And so our first non-linear model non-completely linear model is the TAR model. This is a piecewise linear model in the space of the threshold variable we're working with, which means this is mostly one linear model in one interval and a different linear model in the other case. So if the observation t minus 1 was more than 0, we have this way to calculate the next one, and if the previous one was greater or equal than 0, we will go this way. These are normal 0 ones mostly. Here the delay is one time period, x of t minus 1 is the threshold variable, and the threshold is 0 over here. This threshold divides the range into two regimes or two intervals, which is mostly, this regimes concept is basically the two subintervals in which you divide your observations. That if the threshold is 0, it means we have a model for when our observations are smaller than 0, and a different model where observations are greater than 0. That's what the threshold means in this case. However, what is so special about this model? So first of all, it's asymmetric. Second one, the mean of the observations is not 0, even though there is no constant term in the model. And third one, the first lag coefficient might be greater than 1 in absolute value. As we saw in AR models, having something greater than 1 in absolute value was a big no-no, but here it offers interesting possibilities. I'm going to see some financial applications to this. First one, the nonlinear market model. If we consider monthly log returns of GM stock and Standard & Poor's composite index, the market model is basically this, and for a simple nonlinear model we can apply this, which is basically establishing a threshold 0 and using different coefficients in one side and the other. So how do we model the leverage effect in volatility? We will have to go for exponential guards, T guards, and AP arch models mostly. Now, for a different one, we have Markov switching models. It's a two-state MS model. Call it MS is for Markov switching. And so it is mostly a different type of threshold model, but here our realization, the threshold realization is actually a first order Markov chain, where the transition probabilities is like this. It's a variable that can go from 1 to 2 and from 2 to 1 with certain probabilities. And thus we don't have intervals, but instead realizations of this variable, mostly. And so, of course, the inverse of this probability is the expected duration, the expected of times that you are staying in state 1, and the same for W2. That's elementary property of Markov chains. For an example, we have the growth rate of US quarterly real GNP from 1947 to 1991. These are the estimate coefficients in state 1 and the estimate coefficient in state 2. So, regime 2, in state 2, have a negative expectation or growth, which denotes recession periods, negative periods, regression periods mostly here. The SE of the estimates are large due to the small number of data that we have here, so we really can't thread any lighter because we don't have enough data to do that. Expected durations for regimes 1 and 2 are respectively 8.5 and 3.5 quarters, respectively. Did I say respectively twice? I really hope not. So these two approaches are basically deterministic versus stochastic. They're basically trying to handle similar nonlinearity in a time series. Which one we will use depends heavily on the information we're given. So, for some empirical analysis, you may use the R package TSA to fit tar models. Subcommand is tar, and commodity prices tend to be nonlinear. For example, tar models are generally used to study the annual price of copper from 1800 to 1996. For example, if we use a 2 regime tar 1-2 model with delay 1, this actually fits the data better than an AR12 model, which has, a ton of more coefficients to work with. Now, this for tar models. For Markov switching models, we can use this package here, MSWM. Command is msmfit, and the package mostly uses an EM algorithm to perform estimation and some simulation to produce forecast. The package is the one we use to model this example over here. And this is it for this small introduction to nonlinear models. I will see you in lecture 7 when we will explore these linear models and others in more depth. Thank you very much for joining. Please stay safe, please stay hydrated, and see you in lecture 7.